Have you ever looked up at a skyscraper and noticed that the higher it rises, the thinner it seems to become? At first glance, it looks like an artistic choice, something architects do to make a building appear elegant and modern. But the real reason is far more fascinating. The shape of a skyscraper is often determined by powerful forces that cannot be seen: gravity, wind, and the limits of engineering. By the end of this video, you'll understand why the world's tallest towers narrow as they climb into the sky, and why that design is one of the secrets that makes extreme height possible. When people think about skyscrapers, they usually imagine steel, glass, and concrete. What they don't often think about is the wind. Near the ground, buildings are partially protected by other structures, trees, and obstacles that slow moving air. But as a tower rises hundreds of meters into the atmosphere, it becomes increasingly exposed. Strong winds can push against the sides of a building with enormous force. A skyscraper is not completely rigid. Engineers intentionally allow a small amount of flexibility so the structure can absorb energy, instead of resisting every force like a solid rock. That means tall buildings can sway slightly. The movement is usually tiny, but if it becomes too large, people inside may feel uncomfortable even though the building remains safe. One of the easiest ways to reduce wind force is to reduce the surface area that the wind can push against. A wide tower acts like a giant sail. A narrow tower catches less wind. By making the upper portion of a skyscraper thinner, engineers dramatically reduce the pressure created by strong winds at high altitude. Imagine holding a large sheet of cardboard outside on a windy day. The wind pulls and pushes against the entire surface. Now replace it with a thin board. The force becomes much easier to control. Skyscrapers follow the same principle. A slimmer upper section means less wind resistance and less movement. But wind is only part of the story. As a building gets taller, every additional floor adds more weight. That weight must travel down through columns and structural supports until it reaches the foundation. If the entire tower remained equally wide from bottom to top, the lower structure would have to carry an enormous load. By tapering the building, engineers remove unnecessary weight near the top, reducing the burden on everything below. This creates a more efficient structure. Less material is needed in the upper levels, and the foundation does not have to support as much total mass. The building becomes lighter while still remaining strong, where strength is most needed. There is another important reason skyscrapers become thinner as they rise: stability. A very tall, uniform tower can experience complex wind patterns that create vibrations. Air flowing around the building can produce repeating forces that cause the structure to oscillate. Engineers study these effects carefully because a small vibration can grow stronger if it occurs at the wrong frequency. To solve this problem, architects often change the shape of the tower as it rises. Some buildings taper gradually. Others step inward in several stages. Some even twist as they climb. These variations disrupt the wind patterns that would otherwise create stronger vibrations. One famous engineering solution is the tuned mass damper. This is a huge weight placed near the top of a skyscraper. When the building sways in one direction, the damper moves in the opposite direction, helping to reduce the motion. Many super-tall towers use this technology to improve comfort for the people inside. Even with advanced dampers, however, the shape of the building remains critical. A tapered tower naturally performs better in strong winds than a giant rectangular block of the same height. Modern skyscrapers are also designed with economics in mind. The lower floors of a building are usually the most valuable because they can accommodate large lobbies, retail spaces, and wide office areas. Higher floors often require fewer square meters to remain profitable. This means a narrower upper section can make financial sense as well as structural sense. When architects and engineers begin designing a super tall building, they don't simply draw a beautiful shape and hope it works. They conduct extensive wind tunnel testing. Scale models of the tower are placed in controlled airflow so engineers can observe how air moves around the structure. Computers then simulate thousands of different wind conditions to identify potential problems. Sometimes, even the smallest change in a skyscraper's shape can make an enormous difference. A slight taper near the top, gently rounded corners, or a subtle twist along the height of the building may seem like minor design details, but they can have a major impact on how the structure performs. These features help break up the flow of air around the tower, reducing the pressure created by strong winds and minimizing the vibrations that can develop at extreme heights. Because wind forces increase dramatically as buildings grow taller, improving the tower's aerodynamics can significantly reduce the amount of structural reinforcement required. When engineers succeed in lowering those forces, they often need less steel, less concrete, and fewer massive support elements to keep the building stable. That doesn't just make the structure more efficient, it can also save millions of dollars in construction costs without compromising safety. These seemingly simple design adjustments are the result of years of research, computer simulations, and wind tunnel testing. Every curve, setback, and taper is carefully evaluated before construction begins to ensure the building performs as efficiently as possible. In the world of super tall skyscrapers, smart design isn't just about creating an iconic skyline. It's about using engineering to achieve greater strength, stability, and efficiency with fewer materials. The result is something remarkable. The shape of a skyscraper becomes a conversation between architecture and physics. What appears to be a stylistic choice is often a carefully engineered response to invisible forces. Take a look at many of the world's tallest buildings, and you'll notice something interesting. Very few of them rise straight into the sky as simple rectangular boxes. Instead, they gradually become narrower, step inward at different heights, curve along their sides, or even twist as they climb higher. At first glance, these unique shapes might seem like bold architectural statements, designed purely for visual appeal. While they certainly give each skyscraper its own identity, their true purpose goes far beyond aesthetics. Every change in a building's shape is carefully planned to solve real engineering challenges. As a tower rises higher into the atmosphere, the forces acting on it become increasingly complex. Wind doesn't simply push against a skyscraper in one direction. It flows around the structure, creating swirling air currents and changing pressure on different sides of the building. If the tower had the same shape from bottom to top, these wind patterns could become more organized and produce stronger vibrations. By introducing setbacks, tapered sections, rounded corners, or twisting forms, engineers disrupt the airflow, making it much more difficult for the wind to generate powerful oscillations. These design choices are not based on guesswork. Long before construction begins, architects and structural engineers spend years studying how different shapes behave. They create detailed computer models capable of simulating thousands of weather conditions, from gentle breezes to powerful storms. Scale models are also tested inside wind tunnels, where engineers can observe exactly how air moves around the proposed design. Even a small modification, such as softening a sharp corner or reducing the width of the upper floors, can significantly reduce wind loads and improve the building's overall performance. This is why modern skyscrapers often look so different from one another. Each tower is shaped according to its height, location, surrounding buildings, and the climate in which it will stand. A design that works perfectly in one city may not be the best solution in another. Every curve, every setback, and every taper is the result of countless calculations, experiments, and engineering decisions aimed at creating a structure that is not only beautiful, but also safe, stable, and efficient. So when you admire the silhouette of a super tall skyscraper against the skyline, remember that you're not just looking at an impressive piece of architecture. You're seeing decades of research, innovation, and scientific understanding transformed into a structure that can stand strong against the invisible forces of nature while reaching hundreds of meters into the sky. And here's the surprising part. As engineers push toward even greater heights, the trend toward slimmer towers may continue. Future skyscrapers could become even more tapered, even more aerodynamic, and even more carefully tuned to work with the wind rather than against it. The next time you stand in a city and look up at a towering skyscraper, notice how it changes shape as it rises. That narrowing profile is a reminder that building tall is not just about stacking floors higher and higher. It is about balancing gravity, wind, weight, comfort, efficiency, and human ambition all at the same time. In a way, every tapered skyscraper tells the same story. The higher we reach, the smarter we have to build. And that may be the most impressive thing about these structures. They are not simply monuments of steel and glass. They are carefully crafted solutions to some of the most challenging engineering problems ever faced by humanity. If you enjoyed discovering why skyscrapers get thinner as they get taller, leave a like on the video, subscribe to the channel for more fascinating engineering and science stories, and share your thoughts in the comments. What other hidden secrets of modern architecture would you like to explore next?